So the main contribution of this work is a tool. It's a tool that finds bottlenecks in Java code. We've embedded this tool in the IBM JVM. And if you're able to find the bottleneck inside your code, then you can try and optimize that particular point that caused the trouble. And if you're optimized, then you can go faster and you can save time and you can save money. So nowadays, computers have numerous cores. And we can work with an analogy here. We can think of a computer core running as a car runs on a road. But as you can see, roads sometimes can be shared. So the same thing happens with resources inside computers. So there might be a core that tries to do something, for example, on your USB key, and there might be another thread trying to do the same thing. So if you let them run there on their own, that might lead to problems because they might crash. So in that case, we need to avoid that. We cannot leave threads doing their own stuff on their own. We need to check them a little bit. This is why we're introducing the concept of a lock, which is portrayed here by our policeman over there. So the lock allows only one thread, only one CPU core at a time to exist on a critical section. A critical section is the point in the execution that the threads share that particular resource. So we're using locks. Makes sense. But the problem with locks, of course, is that they cause traffic. In the same way that our policeman over there needs to stop one of the currents, one of the currents, this immediately causes one car after the other to stop there. So this is called a bottleneck. As you can see, we have the wine bottle over there as an example. So yeah, in the same way that if you take a bottle of wine and you turn it upside down, it's not going to empty immediately, right? Because it's the nozzle at the end that prevents the flow to be that fast. Sometimes it's good, sometimes it's bad. Yeah, if you want to drink very fast, it's probably bad. You get the point. So what happens, technically? Whenever threads need to wait on the critical sections, on locks, we say that they are parked. And this is what actually pretty much is happening. It's an analogy. And as long as they are parked, they're not working. So we have our cores, but they're there and they're not doing anything useful. So this is something that we need to know because we'd rather have our processors working all the time, right? We don't want them to simply stay there doing nothing. So what we did is we modified the IBM JVM in order to measure time and other related metrics concerning parking contention. So for example, here, you can see that there are 3 threads parked on that block. So the first one has been waiting for 9 seconds, the second for 5, the third for 1. We're able to calculate these metrics, and then we can provide them to the user, and the user can see which bottleneck can cause the most trouble. For example, here we have 2 bottlenecks. So there are 2 intersections, and one is a little bit more contested than the other. So we can see, for example, that the left one has 15 seconds of total contention, whereas the right one has only 2. So if we're trying to optimize a code, we should go for the left one. There's no point in trying to optimize the right one, right? It's already doing fairly well in comparison to the other one. So that's the core idea, that's the main idea here. A little bit of technical background on where we're working. So Java, this is our platform. This is the language that we're using. It's a programming language. It's machine independent, and it's machine independent because instead of running directly on the computer hardware, there's a program that runs Java. This is called the Java Virtual Machine. So what we have is different versions of the JVM for different platforms and different architectures. So the Java part remains constant, whereas the part that speaks to the OS and the processor changes. In particular, we have a library, as always in computer science. We try to avoid reinventing the wheel, right? And we'd rather use everything that's there available already. That library is called the Java Util Concurrent, JUC, and it's the most important and standard concurrency library for parallel features and multi-core features in general. One of the main things in there are JUC logs, and these are the logs that we're trying to monitor and find bottlenecks with. There are also other interesting concurrent programming tools, and we're also gathering data on that, but that's for another topic, another day to discuss on. So this is what we did. We created a tool. We call it the JUC part contention tool. And the motivation behind this is that there was no such tool embedded inside a JVM that could provide this kind of part-related metrics. So we formulated a hypothesis. This is science, right? So we had to follow a scientific method. And the hypothesis is that what if we had such a tool? Would this provide us with the opportunity to find bottlenecks and consequently accelerate our code? Well, finally we'll see that our hypothesis was confirmed. But let's not jump into conclusions yet. So what we did concerning our methodology. Initially, we decided on what kind of metrics we're going to provide. We modified the JVM of IBM. We also had to measure the induced overhead. This is very important because we're modifying a production VM. So we do not want to make the VM to be super slow because nobody would want to use it afterwards. I mean, the idea is to make everything faster, not change it and make it worse than before. And finally, we were able to use some examples and show the usefulness of our metrics. So let's discuss a little bit of our metrics. We have the thread par time. So this is the sum of all the parking times that all the threads had to wait on a particular lock. For example, if we have 1, 5, and 9 seconds for that lock over there, the thread par time is 15 seconds. We also have the peak part threads. So this is the maximum number of threads that had to wait for that particular lock. So the traffic reached its maximum at some particular point. Well, how long was that? In our case, it's 3. We also keep the real parking time, which is equivalent to the holding time, and it's for how long the lock was held by some of the threads that are passing. Because while a thread is passing through the intersection, it actually has the lock. We have some more metrics. They're relative metrics this time, so they're derived from the ones that we had before. So suppose that we have an execution time of 10 seconds in our example. So the thread time utilization would be the thread time over the execution time. So in our example, 150%. It's over 100, but that's fine because we have multiple threads running at the same time. We also have the real-time utilization, which is in our example 9 seconds over 10 seconds. So this is 90%. This means that this particular lock was locked 90% of the execution of the application. And we also have the average hold time. And in that case, we're dividing the 9 seconds with the number of cars that had to wait. So we can figure out what's the average time a lock was held. We also provide some more metrics, but these are some of the core metrics that we have. So let's see an example. Suppose we have 3 critical sections that are being protected by 3 JUC locks. We have 64 threads, which are the cars for our analogy, and they go around it all the time around. So there's a little bit of a difference. So the junctions are causing different breaking times for our threads. So we have the first thread, the green one, the first block, the green one, that blocks threads for 4 milliseconds. The second one, the red, blocks them for 16. The third one, the blue, blocks them for 64. So in that case, we need to find out which junction is the most congested. I mean, we're expecting all the cars to be accumulated in one of the 3 places. So which is the lock that bottlenecks the code? So this is the important part. This is what our tool provides. We were able to run this experiment with our tool switched on. And as you can see, lock number 3 has significantly larger metrics, contention metrics. I mean, it's you can see the radar as well, but don't be fooled. This is a logarithmic radar. Initially, I had drawn this with a linear scale, and there were just dots for the green and the red one. So our tool was able to clearly find the bottleneck here. I mean, we were expecting the 64 millisecond one to be the problem, but you can see here that it's actually working properly. And also one more thing to show here, if I can find a way to use this. No? But that's fine. I have an arrow over there, the blue arrow, concerning the average hold time. You can also see that the estimation that we were able to give is very close to the actual number. So we had 64 seconds, and you can see here that we're very close. We went to 59.48. For the second lock, we had 16 milliseconds, and this is 16.24. And for the third, 4.3. So not only were we able to find bottlenecks, but we're also able to estimate the average hold time quite accurately with our method. But some will say, yeah, sure, we can optimize all of the critical sections. Yeah, but if you have 100 of them, which one should you optimize? It doesn't work like that. So if you try to optimize critical sections that are not the bottleneck, you're not getting anything. So you've actually worked for nothing. And we tried that. So we tried to optimize all 3 locks by halving the waiting time. And we're printing here the speed up. So this is how faster the application went after we tried the optimization, one by one. And when we tried to optimize the non-bottleneck locks, we got 1, which means that it was as fast as before. Nothing happened. But when we optimized the lock that was the bottleneck, we were able to get a speed up of almost 2, 1.96 in particular. So our tool is useful. You cannot simply go and try and optimize everything. And usually you don't only have 3 bottlenecks in your code. You might have 100, you might have 1,000. Locks are very important. Shared resources are everywhere in computers nowadays. So in conclusion, what we did is we provided a tool. This tool is embedded in the IBM JVM, and it's measuring JUC part-related metrics. We also measure our overhead. It's negligible. It's practically 0. We implemented this in a general way, so it doesn't really matter that it's for the IBM JVM at the moment. If somebody reads through our paper and through the thesis, they can go ahead and implement that stuff, although we're filing for a patent at the moment. We were able to find JUC lock bottlenecks, as you've seen with the example we discussed before, and that leads to substantial optimization, and we can use as indicators high real-time utilization, thread time utilization, and peak part. So those are some of the metrics that we discussed before. And we were also able to estimate quite accurately the average hold time. And this is it.
You try to optimize the Java applications or optimize JVM itself?
We're trying to optimize Java applications. So we're expecting...
Every application you're looking for, you can optimize that application based on the current.
Exactly. So if they're using JUC locks and they might have made a mistake somewhere, our tool can potentially find it. So they might, for example, be inside a critical section and doing stuff that they shouldn't be doing.
You're not changing the JVM at all.
We changed the JVM because we modified it to monitor what's going on. So threads are being parked just before they are parked and right after they're parked. We had a little bit of code there, and we're saying this is when it got in, this is when it got out. That's the difference. Let's add it somewhere.
When you say that it is now going faster, what do you mean by that? Because if they are parked, they are waiting maybe for another process, or they are just there. What are they doing when they're during the waiting time? Is that when you say that they're faster, the waiting time is reduced?
So what's going on is if the threads are being serialized, they have to wait one after the other. So at this point, if we have 10 processors, we're only using 1 because all other 9 processors are blocked. They're parked. So it's as if we're going back 10 years in the past and having still a single core CPU. That's the problem. That's the issue here. It kills our main way of finding power nowadays, which is parallelism.